Welcome to this video on concave and convex functions. I'll first define rigorously what they are, and then I'll take you through a process of how to determine functions are concave and convex by analyzing the Hessian matrix of that function. And not only am I going to show you how to do that practically, I'm also going to derive and explain why that shows the analysis on the Hessian matrix, why that shows a function is concave or convex. So I'll take you through the proof and the derivation as well. So there'll be a lot to this video, but I hope you find it helpful in understanding functions and what makes them concave and convex. All right, let's get into the video. So a concave and a convex function, I'm going to start back to front. It looks like this. Concave looks like a cave you can go into. And then convex looks like this bow shape, which is just concave upside down. And we want to define how to identify functions that have this shape. And to do that, there's this very technical definition for it. And that is, as you look at the points in between 2 points for the function, so we take x and y and we look at the points in between it, then there's going to be a specific property that's taking place here. And that is that the combination of x and y plugged into the function will always be above the mixture of x and y evaluated within the function. So it's this analysis of combining x and y and then plugging it into the function, that's the green, compared to f of x and fy and the combination of that, which is the orange line here. And this is a measuring stick to see, is the convex combination of fx and fy always above or below the convex combination of x and y plugged into the function. So we're analyzing in between x and y, is that plugged into the function above or below the combination of fx and fy. So fx and fy here, combination in between, x and y combination in between. How does that go in the function? And that's how the definition goes. So a function is concave if the combination of x and y is always greater or equal to lambda fx plus 1 minus lambda fy when that combination is plugged into the function. And a function is convex if this inequality is flipped the other way around. That's pretty much it. So that's how we define concave and convex functions. If they follow this rule, then they will always have this shape of a cave or a smiley face, depending on if you're looking at concavity or convexity. Okay, so why do we care about this? Well, we want to know if things are concave or convex because in optimization settings, we're usually looking for maxima or minima. And if your cost function looks like this, then we care about finding the lowest point. And if your profit function looks like this, we care about finding the highest point. And all of this is building into understanding our objective functions and what shape they have so that we can optimize those functions. That's essentially our goal here. Okay, so now we've got this definition of what they are. How can we find them? How can we determine functions are concave or convex mathematically? Well, first, let me just explain something. If you follow this logic chain, then it will ultimately lead us to how the Hessian matrix will reveal if the function is concave or convex. But bear with me first as I just introduce to you a few different concepts. We've got epigraph and hypergraph. They are sets that lie above or below a function. And if your function is concave like this, then the epigraph is above this function here. And the idea is that our hyperplane, our tangent to this function, will always be contained within that epigraph. So every time you draw a tangent to this concave function, you'll always find that those points will lie in between the whole set that is above the function here. Okay, so for concave functions, the tangent hyperplane is always above the function. And that means that f of x, which is this curve here, is always less than or equal to the tangent hyperplane which is defined inside of this red box. And we have a comparable theorem for convex functions, that it's always above the tangent hyperplane. Okay, so our second order conditions for concavity and convexity are related to this idea. We can determine a function is concave or convex by comparing the function to its tangent hyperplane. And previously, well, maybe not in this video if you've seen previous videos, we've looked at the second order Taylor approximation for something, and a function can be approximated by the second order Taylor approximation of this. So fx is approximately equal to this, and the first part of this Taylor approximation is the tangent hyperplane, and the second part of the approximation is the quadratic component here. Okay, and the theorem we're looking at above, it's relating fx to the tangent hyperplane. So we just have this extra part here, the quadratic component that is going on right now. And if we do some rearranging, we get fx minus the tangent hyperplane is approximately equal to this quadratic component of the Taylor approximation. Okay, and that means that the difference between f and the tangent hyperplane, if it's less than or equal to 0, we know that f is concave. And if this quadratic component is less than or equal to 0, that will imply that that is true. So essentially we can focus our analysis on this by instead analyzing the quadratic component here. Okay? Now, I know that can be confusing, so I've rewritten it again in simple terms. So let's just go through the idea here. If f in the circle denotes the function, t in the circle denotes the tangent hyperplane, and q denotes the quadratic component of the second order Taylor approximation, then this is what we're doing. We care about if f is less than or equal to t, if the function is less than the tangent hyperplane, because if that's true, we know that it's concave. And rearranging that means that we want f minus t to be less than or equal to 0. That will imply that's concave. And we know that f minus t is equal to something else, and we're trying to analyze if that something else is less than or equal to 0. And in this case, the something else is that quadratic component. So if quadratic component is less than or equal to 0, then f minus t is less than or equal to 0, then f is less than or equal to t, which means f is concave. Now, there's one thing we should clarify as well, and that is that we only have an approximation with the Taylor series. So f is only approximately equal to the tangent hyperplane plus the quadratic component. But the punchline of what's written below is that that doesn't affect the narrative of this analysis. The error will go to 0 fast enough that it doesn't actually affect the analysis at all. So practically, we can use this for the intuition of our theorem, because in practice, it doesn't matter, and intuitively, it makes sense. Okay, so based off this above, we can now analyze if the function is concave by just analyzing this quadratic component. Is this quadratic component less than or equal to 0 or greater or equal to 0? And what the answer is to that question will determine if the function is concave or convex. And once again, we can take it one step further into simply analyzing the Hessian matrix. If we can understand how that Hessian matrix operates, we can answer if it's always going to be less than or equal to 0 or greater or equal to 0, or varying, which means that it's neither convex nor concave. Okay, I know this is a lot, but if we keep going, the analysis as to whether this is less than or equal to 0 or greater or equal to 0 depends on here how the matrix operates. So the Hessian matrix, if you are unfamiliar or have forgotten, is equal to the matrix of second order derivatives, like this. And I suppose there should be a transpose here. And we're just analyzing how this matrix is as to how that will affect things in this equation. And there's a bunch of theorems that show if A in its definiteness is positive definite, then this will always be greater or equal to 0, so on and so forth. So we go to this next slide. These theorems say that if the matrix A is positive definite, that implies that this is greater or equal to 0 for all x that's not 0. And we know the matrix is positive definite if the leading principal minors are all greater than 0. And there's another one for being negative definite, which means that it's less than 0. And then there's indefinite, which means it's neither. And then there's semi-definite, negative semi-definite, etc. And I'll talk more about that in a second. But the idea is that if we can classify if the Hessian is positive definite or negative definite, we know that this is true. And if we know that this is true, we know how this equation turns out in terms of being less than or equal to 0 or greater or equal to 0. And if we know that and we work backwards, we get f being concave or convex. So now we can analyze if a function is concave or convex by simply analyzing the Hessian matrix and its definiteness. Okay, that's the derivation, at least intuitively, of how to work out if a matrix is concave or convex. If you are unfamiliar with the details of this process, and then you're more focused on understanding what that is, then you have to learn the mechanics of this. There's no way around it. You have to work out how to work out the principal minors, and then once you know that, you just plug it into this mess and you see what the principal minors do in terms of these theorems, and then you just match it to one of them. So to work out principal minors, let's just take a look at that. Principal minors are used to analyze a matrix. If your matrix is defined in this way, then the principal minors are just defined as this. That's it. So the first principal minors are the determinant A, E, and I. The second principal minors are the determinants A, B, D, E, A, C, G, I, and E, F, H, I. And the third principal minor is the determinant of the whole thing. And then the leading principal minors are these first three here, which is the determinant of that, the determinant of that, and the determinant of that. Those are your leading principal minors. And that's just the mechanical definition of what they are. And once you have them, you then compare those determinants of the leading principal minors to this. So if the determinants in red here are all greater than 0, then that will show that it's positive definite because this here is true, which implies positive definite. That's it. And there's a quick determinant refresher below, and there's another video that I've made that explains how to calculate determinants as well. Okay, but I won't focus on the logistics of that too much. I just cut to an example and then finish off the video. So in this example, we're given this function here, and we want to analyze if it's concave or convex. And to do that, we can calculate the Hessian matrix. So actually, this is different again. So this is not an analysis on the Hessian matrix, this is analysis on the quadratic directly. So you can combine here these variables into a quadratic form directly like this, taking the squared terms there and the cross terms, halving it and putting it like so. Once you have this matrix, you can calculate the principal minors. And because you have D3 equal to 0, we need to calculate every principal minor, which is done below. And once you calculate all of them, you find that all of them are positive or 0. And if you go up to our chart, then positive semi-definite is that every principal minor is greater or equal to 0. So the semi-definite is what allows us to have greater or equal to, as opposed to positive definite, which is strictly greater on the leading ones. Anyway, you can pause the video and have a look through the maths of that if you please. Okay, last slide, just to summarize everything that we've looked at. So say you have a function f and you're trying to classify the critical points of that function, and in doing so you want to know the definiteness of the matrix to evaluate if it's concave or convex. Here's a chart to summarize what that is. So you calculate the leading principal minors D1, D2, and D3, and then you classify them according to the system below. If all the leading principal minors are greater than 0, we know that it's positive definite at x star, which means f is strictly convex at x star, which means x is a strict local minimum of f. And that looks like this shape here in 2D. Notice that it's not double arrows because you can be convex without being strictly positive definite. But if it is positive definite, you know that it's convex. Option 2, if you follow this pattern of leading principal minors being negative, positive, negative, then that goes into being negative definite, strictly concave, and a local max. Here, you've got positive semi-definite and negative semi-definite, which requires analysis on all the principal minors, not just the leading ones. And that will be important to do. And if H is semi-definite, then the second order test is inconclusive. So if you get any of these ones above, then we can't use the second order derivatives to tell if it's max or min. And then the fourth one is that if it's none of the above, then the Hessian matrix is indefinite, and that makes it a saddle point. Sorry that the scan is faded. So if it's none of the above, if it's not semi-definite, positive definite, or negative definite, then it's indefinite, and so it's a saddle point. Okay, and ultimately we're just using this chart and interpreting it here. Okay, so that's the video on concavity and convexity and how to determine that from our Hessian matrix, as well as a deeper understanding of why that actually allows us to know if the function is concave or convex. And it's useful in many different settings in economics, especially in optimization. Right, I hope you found this video helpful. Thank you for watching.